In this lecture, we will talk about how to implement directories, and we'll also talk about various allocation methods. So a directory can be implemented in one of two ways. We are going to talk about a linear list and a hash table technique. So a linear list is essentially a list of file names with pointers to the data block. So a directory, which is a special type of file because all it contains is the information about all the files and subdirectories inside that directory. It right now in the linear list, it has a list of file names with including the pointer to the data blocks where they are located in the hard disk, and it's going to be a linear list. And because it's a linear list, it is very simple to program. However, the time consumed to do a search for a particular file name is going to be long because it's a linear search time. So if you're trying to search for the first file in the list, it's going to be very fast, but 50th file in the list is going to take you 50 times longer because it's arranged in the form of a linear list. So we could have algorithms that search to make our time or latency lower. So we could keep an ordered alphabetically list via linked list or a B plus tree. But the major drawback here is the time it takes to find a file or to verify whether one exists or not. The alternate to that is the hash table, which is a linear list with hash data structure. So a data structure which takes in a file name and gives an output of the file location. So it decreases the directory search time tremendously. However, collisions is one of the problems. So collisions are situations where two file names hash to the same location. So these are two ways how you could run a directory organization. So next we'll take a look at allocation methods. So we are essentially going to go through three different methods of allocating disk space to files. We'll talk about contiguous, then we'll talk about linked list, and then we'll talk about indexed allocation. Allocation method refers to how disk blocks are allocated for files. So in this picture over here, we are seeing a cylinder which is representative of a disk. And we are showing different blocks numbered from 0 to 31. So there are 32 blocks of 32 blocks in the hard disk, and each block could be used for a file. So for example, we have a few files here in this particular directory. We have 1, 2, 3, 4, 5 files with file names count, tr, mail, list, and f, and their start block location is given as 0, 14, and so on, and their lengths are given. And in contiguous allocation, this is the case over here, all we need is the start block and the length in terms of number of blocks for each file. So for example, the file count starts at 0 and it goes for 2 blocks, and then the file with file name f starts at 6 and goes for 2 blocks, and then you can run down all the files here. So it is each file block occupies a set of contiguous blocks. As you can see here, all these blocks that are assigned to a particular file name, they are contiguous blocks, and there is no break in that allocation. So there are some good things that come out of this, but there are also some negatives. So performance is very fast because reading successive blocks of the same file generally requires no movement of the disk heads, or at most one small step to the next adjacent cylinder on the hard disk. So that's why it's considered to be best performance in most cases. But problems can arise when files grow or if the exact size of a file is unknown at creation time. So overestimation of the file's final size increases external fragmentation and wastes disk space. So as you can see here, there are several blocks that have been fragmented, which is not a desirable thing. And on the other hand, if you have underestimation of the final file size, that may require that a file be moved or a process aborted if the file grows beyond its originally allocated space. If a file grows slowly over a long period of time and the total final space must be allocated initially, then a lot of space becomes unusable before the file fills the space. So that is not a very good utilization of the memory. Another drawback here is the need for compaction, either offline or online. Compaction is a process of making free blocks into contiguous blocks so that we can fit in bigger files in those spaces. So we will need compaction when we do contiguous allocation. Another good thing about contiguous allocation is even if there is a certain virus that corrupts a particular block, the remaining blocks will be still intact. So it's not like we are going to lose the complete file, although even though there are some blocks that might be corrupted. So we'll still have some data of the file that is preserved. Extent-based files are an alternate to contiguous allocation. So a variation is to allocate file space in large contiguous chunks. They are called extents. When a file outgrows its original extent, then an additional one is allocated. The high-performance file system Veritas, which is supported by Linux, uses extents to optimize performance. So next, let us take a look at linked allocation method. Disk files can be stored as linked list with the expense of the storage space consumed by each link. In the linked list, each block contains data of the file and pointer to the next block. Linked allocation involves no external fragmentation, does not require pre-known file sizes, and allows files to grow dynamically at any time. Unfortunately, linked allocation is only efficient for sequential access files, as random access requires starting at the beginning of the list for each new location access. Allocating clusters of blocks reduces the space wasted by pointers at the cost of internal fragmentation. Another big problem with linked allocation is the reliability of if a pointer is lost or damaged. A doubly linked list provide some protection at the cost of additional overhead and wasted space. So those were some of the advantages and disadvantages of a linked allocation. Let's take a look at how it works over here. So there is one file with the file name Jeep in the directory that is, and all the information that we need is the starting block and the ending block. And if we start accessing the first block, 9, we are going to look at block number 9, which contains part of the data of that file Jeep, but it also contains the pointer to the next block. So in this case, it is going to go from block 9 to 13 to 16 to 1 to 6 to block 10 to block 18 to block 25, which is the ending block. So that particular link is the linked allocation. So all those blocks have two things. One is part of the file and the other is the pointer to the next block. One problem that could happen over here is if the link breaks, then we lose the good portion of the file. So we can go for the doubly linked approach that we used for UNIX file system inode, in which we had single pointers, doubly linked pointers, and triple linked pointers. So we could use that approach to kind of overcome that problem. But in this case, all we need is the start and end block number, and everything else is linked. Now let's talk about indexed allocation. So in indexed allocation, we have each file which has its own index blocks of pointers to its data blocks. So as we can see over here, there are several files on the left, Jeep, file 1, file 2, and so on. And in this particular index table, there is a mapping of each file to its index block. And at its index block, there will be pointers to all of its data blocks. So let's take a look at the example over here. So essentially what we are doing is we are combining all the indices for accessing each file into a common block called the index block for that particular file, as opposed to spreading them all over the disk. So in this picture, we can see how the file Jeep, which has the index block 19, and if we go and look into block 19, we can take a look at the pointers to all the data blocks. So this particular file Jeep is present at blocks 9, 16, and so on up to 25, and 3 of the blocks are not being used because in this case we have 8 blocks per index file, per index block. So clearly some disk space is wasted because an entire index block must be allocated to each file regardless of how many data blocks the file contains. So this actually leads us to questions of how big the index block should be and how it should be implemented. So let's take a look at that with how Unix does it in its Unix file system. So the inode, which is essentially carrying the metadata information for each file, has direct blocks, single indirect blocks, double indirect blocks, and triple indirect blocks. And there's a big advantage of doing this because we can access small files very, very quickly. And if we have a very, very large file, then it's going to take us some time, but it's going to be an increment of time, so a slow increment of time. But by doing this, we can have a very, very large amount of file that we can have on the hard disk. So let's see how to understand this inode structure for Unix file system. So there are direct blocks, as you can see here, and direct blocks essentially have 12 or so data block pointers. So essentially, if you have 12 pointers to a data block, and if the file is small enough to fit those 12 data blocks, then we are done. And all we have to do is take a look at those pointers and access those 12 blocks. So files up to a size of 48K, if we assume a 4 kilobyte block size, we can fit using just the direct blocks, which are going to be cached, so they can be accessed very, very quickly. Now, if the file size is a little bit larger, then we are going to use direct blocks as well as the single indirect. So a single indirect is essentially there is a pointer to a block which contains pointers to where the data is. And in this case, files up to the sum of these two sizes can be used using direct plus single indirect. So the 48K number is coming from direct blocks, which was already there. So that was 4K times 12. And then we add the number of pointers that are being used, 1024, and we obtain 1024 by simply dividing the 4K. We have 4 bytes per pointer, so we need 4 bytes to associate a pointer, so a 32-bit address, if you will. And if we have 4K as the block size, then the number of pointers at each block would be 1024. So 1024 pointers over here times 4K for each of those blocks, that would give us all the single indirect blocks. So file sizes that are up to 4144 KB can be used for direct and single indirect. And then as you keep going further, as you can see here, those numbers of pointers will square and cube, and they will increase. So you can fit in bigger files that way. So in this particular example, we are assuming that our pointer requires 4 bytes or 32-bit address, and the block size is 4 KB. So that's as far as the allocation schemes are concerned. Next, we will talk about free space management.